Hi, I'm Joran Borger, a master's student from the University of Groningen, and in my research project I studied the effect of a contextual banded worst-case estimator on reinforcement learning traffic signal controllers, with the goal of making them more robust. In particular, I focus on improving how these systems perform under difficult or unexpected traffic conditions, rather than only optimizing for average performance. To achieve this, I use a three-stage training framework. First, we train a baseline reinforcement learning controller, such as PPO, IA2C, MA2C or IQLR, on standard traffic demand. Next, we introduce a contextual banded worst-case estimator, which learns to identify challenging traffic scenarios and assigns higher importance to them. Finally, we retrain the controller using these more difficult demand mixtures, effectively stress testing the system and improving its worst-case performance. The experiments are conducted on a synthetic 5x5 traffic grid consisting of 25 intersections, where each intersection is controlled by an individual agent. The network includes horizontal arterial roads with 2 lanes and vertical avenues with 1 lane. We simulate traffic using the Sumo simulator with a control step of 5 seconds and train the agents over a long horizon to allow stable learning. Each traffic light is modeled as an agent with simple but informative interface. The agent observes features such as the number of approaching vehicles, called the wave, and the cumulative waiting time. Based on this, it selects one of 5 possible signal phases. The reward function penalizes queue lengths and waiting times, encouraging efficient traffic flow. You evaluate multiple types of reinforcement learning algorithms, including policy-based, actor-critic, and value-based methods. The key contribution is the contextual banded worst-case estimator. This estimator learns a policy that selects mixture weights over different traffic demand scenarios, and its objective is to emphasize scenarios where the controller performs poorly. So effectively, it learns to focus on high congestion scenarios. Over time, this means that more difficult traffic patterns are sampled more frequently during training. The estimator interacts with the environment at a higher level. It observes the overall network state, including traffic conditions across all intersections, and outputs a probability distribution over demand scenarios. These scenarios are then used to evaluate the controller. If the controller performs poorly, the estimator receives a higher reward, reinforcing the selection of challenging scenarios. So in essence, it actively searches for the controller's weaknesses. For evaluation, we test the controllers on 11 demand scenarios that were seen during training, as well as 1 additional unseen scenario to assess generalization. Each scenario is simulated for 1 hour with multiple independent runs to account for randomness. We measure performance using metrics such as queue length and average speed, both over time and as average values, with the main goal being to improve worst-case performance while maintaining or ideally improving average performance. Here we see the results for the PPO algorithm. The key takeaway is that robust retraining leads to very large improvements. Queue lengths are significantly reduced across all demand groups, and average speeds increase substantially. Most importantly, the worst-case scenarios improve drastically, which is exactly what the method is designed to target. Interestingly, these improvements also carry over to average performance, showing that focusing on difficult scenarios can benefit overall system efficiency. Now we go on to a video of the real-life setup to show you how these algorithms are being trained.
And how does it work for each traffic controller in this Sumo platform?
Yeah, so in this Sumo platform, the nice thing about this is we can assign a controller to each intersection. So we can allow our reinforcement learning controller to control the traffic lights. And so if we let the simulation run and we look at, in particular, at this traffic intersection, we can see that these traffic lights continuously switch. They keep performing a different action. And this is the reinforcement learning agent learning how to control the policy. So right now, the actions that it takes are not per se optimal, but it's doing its best according to what it currently thinks is the best action. But during this, it collects all of these rewards, and it will learn from whatever actions it's taking.
The last question: how did you evaluate the performance during the training?
Yeah. So for that, we'd like to go to our second monitor. This is a thing called TensorBoard. So here on TensorBoard, it visualizes the data that we would like to see during training. So we have a lot of plots about our loss functions, which can be important to look at to see if the algorithm is working properly. But in reinforcement learning, I think the most important thing to look at is our reward during training. So as explained before, we calculate this reward during the training, and we can see from here, from this graph, is that at the start our algorithm is still learning. So it's still trying a lot of different things, of which it's not certain that it's correct. So we see that the reward, the graph drops, which means that it's performing worse and worse. So it's using an incorrect policy. But at some point it will understand which actions are good to take, so it will climb. Sometimes the performance will drop again because it's just trying a few new things, but in the end we can see that it starts getting to a consistent value, being quite stable, and that means that the controller has managed to find a policy to its maximum potential.
Do you realize all the time, or you will turn it off when you're training?
Yeah, so this visualization tool that we use here from Zumo is only being used for us to test if everything is going well, because it's quite computationally expensive to visualize it all the time. Normally we don't do this visualization and we just let it run, and the only way we are checking if everything is going correctly is using our TensorBoard interface, and so there won't be any simulation going on. Well, there will be simulation going on, but it won't be visualized for the user.
Compared with the baseline model, can you show me the improvement after retraining?
Yes. So before this, we've already trained all of our models, and so we can show you guys some videos of this. Here we can see a video of each controller. So first off, here we see the video of the baseline PPO controller on its most difficult group. As we can see, there is a lot of congestion happening, and so a lot of cars are being queued up. This is because the PPO controller is supposed to learn a policy for a wide range of demand groups. And here we can see that it has struggled to find a good policy to handle with this group. Here we can see the video of the retrained PPO controller, the exact same demand group. Here we can see that there's almost no congestion happening and that the flow of the vehicles is much better. This means that the PPO controller was able to adapt its policy to also have a correct policy for its worst performing group, showing that implementing the worst case estimation does indeed increase performance.